Welcome to my online course in linear algebra for undergraduate mathematics. Today we are going to discuss about norm function and its property. Let X be an inner product space. We define norm from X to her by norm of X is equal to inner product of X comma X square root of inner product of X comma X for all X belongs to X. Then the following are satisfied. Number one, norm of X is greater than equal to 0 for all X belongs to X. Norm of X is equal to 0 if and only if X is equal to theta for all X belongs to X. Next property, now norm of X alpha X is equal to modulus of alpha norm of X for all X belongs to X and alpha belongs to C. Third property, modulus of inner product of X comma Y is less than equal to norm of X norm of Y for all X comma Y belongs to X. This property is known as Schwarz inequality. Fourth property, norm of X plus Y is less than equal to norm of X plus norm of Y. Fifth property, norm of X plus Y whole square plus norm of X minus Y whole square is equal to 2 norm of X square plus 2 no twice norm of Y square. This property is known as parallelogram law. Now next we are going to prove these properties. Number one, norm of X is my square root of inner product of X comma X which is greater than equal to 0 if for all X belongs to X. Okay. Next, norm of X is my square root of inner product of X comma X which is equal to 0 if and only if my vector X is my null vector. If and only if X is my null vector. Number two, norm of alpha X is my square root of inner product of alpha X comma alpha X. From this, take alpha outside of the inner product space from the first element. Again from the second element, I will get alpha bar. From the second element, when I will take alpha outside, then it will be conjugate of alpha. Again, by using properties of complex number, alpha bar is my modulus of alpha square. That is, in the next step, it is equal to square root of modulus of alpha square inner product of X comma X. Now take modulus of alpha outside. This will be, in the next step, it will be modulus of alpha square root of inner product of X comma X. By definition, we know that this is equal to my norm of X. Therefore, this step will be equal to this one. That is modulus of alpha norm of X. Next, third property. Third one, we are going to prove third one, that is modulus of inner product of X comma Y is less than equal to norm of X norm of Y for all X comma Y belongs to X. For that, we consider that none of this vector XY is null vector. If any one of them is null vector, then what happens? Then with at least one vector, suppose X equal to my theta vector, then theta into Y, inner product of theta into Y is 0 for all Y belongs to X. So here I am getting this equal to 0 and norm of null vector is 0, norm of theta which is my 0, which is my 0. So 0 multiplied with any norm is nothing but distance. So 0 multiplied with norm of Y is my 0. So we have considered X is not equal to theta and Y is not equal to theta. Then we are proceeding with the proof. Now, that is, yeah. If at least one vector X and Y is the null vector, then the result hold with equality. So consider X not equal to theta and Y not equal to theta. We have considered inner product of Y comma Y is equal to alpha and inner product of X comma Y is my beta. We have considered alphas here. Y is non-null, so alpha is greater than 0, and we have considered alpha in such a way that alpha is equal to alpha conjugate. Okay, then trivially we can check out that norm of alpha X minus beta Y is greater than equal to 0, which you should take norm of alpha X minus beta Y whole beta Y square is equal to inner product of alpha X minus beta y alpha x comma alpha x minus beta y. On expansion, I will get this one multiply the take inner product of this one with this one, then this one with this one, then this one with this one, inner product of the with this one. This is the expansion. This is the expansion. So from the first element, I am taking alpha outside. From the second, when I take alpha outside, it is conjugate of alpha. Then I will left with inner product of x comma x. Next, from here I am taking alpha outside. From here I am taking minus beta outside. When I take minus beta outside, it is minus beta bar beta conjugate, and within the inner product we have x comma y. Likewise, from this term I am taking minus beta and alpha outside, then it is alpha conjugate, and this is inner product of y comma x. Here I am taking minus minus will be plus, that is beta beta bar, inner product of y comma y bar. Here it is alpha alpha conjugate is my magnitude of alpha square, inner product of x comma x is my norm of x square, minus alpha beta conjugate inner product of xy minus beta alpha alpha conjugate inner product of y comma x plus this is modulus of beta square beta modulus of beta square norm of y square y whole square. From here it is inner product of xy is my beta, so in place of xy I'm going to put, in place of this I'm going to put beta. Here we know that this is equal to, from the second exam in the definition of inner product space, this is my conjugate of this one, and this is my conjugate of beta bar. So this term finally will be alpha beta beta conjugate, and this term will be my minus beta alpha conjugate beta conjugate. So these two terms will give you minus 2 alpha beta beta conjugate. Here this beta conjugate will be minus 2. This is equal to 2 alpha beta whole square. So in this place I am putting, substituting step here. Here this is minus 2 alpha. This here norm of y square is my inner product of y comma y, that is alpha, so I am putting this alpha here. I am getting this one. Is it okay? How can I will get this one? I have explained here. Explain here. Then by since this due to this I am getting this one. So this is minus 2 alpha beta modulus of beta square. This is plus alpha modulus of beta square. I will get minus alpha beta square. This term will left as it is. Okay. From here I will take alpha common. From this term I will take alpha common. This is alpha, within bracket it is alpha norm of x square minus norm of modulus of beta square. This is greater than equal to 0. Since alpha is greater than equal to 0, so I have this one is greater than equal to 0. If this one is minus 0 minus, then it will be less than equal to 0. So both the term will be greater than 0. Either both the term will be greater than 0 or both the term will be less than 0. Here alpha is greater than 0, so this term must be greater than 0. So in the next step, alpha norm of x square is left. I'm bringing the minus beta square modulus of beta square to right hand side. I will get this equation. Okay. Now since alpha is my inner norm of x square is my alpha, so in place of alpha I am putting norm of x square. This is no multiplied with norm of y square. This is modulus of beta square, as beta is greater than 0, greater than equal to 0. What is beta? Beta is the inner product of xy. Inner product of xy is greater than equal to 0 for all xy, and it is equal to 0 if and only if x and y both are null vector. Since it is null, so the modulus of beta is greater than equal to 0, and norm of vector is greater than equal to 0. So we will get this one. This implies modulus of beta is less than equal to norm of x, norm of y. What is beta? Beta is my inner product of xy. This one, inner product of xy. So in place of this, I am getting this one. Modulus of inner product of xy is less than equal to norm of x, norm of y. Now I am going to prove the fourth property. What is fourth property? Fourth property is inner product of x plus y is less than equal to inner product of x plus inner product of y. The norm of x plus y whole square. This is equal to inner product of x plus y comma x plus y. On expansion, I will get this one. I will get this one by using the definition second axiom of the definition of inner product space. I can write in place of this, I can write this one, and here in place of this I can write inner product space, and then here in place of this I am writing it inner product space. Sorry, this is norm of x square, this is norm of y square. Now I am considering x plus y equal to a plus b, a plus ib, as inner product of xy is my complex number, so I consider it as the complex number a plus ib, where n p are the real number. In case of complex number, we know that if z equal to x plus iy is a complex number, then modulus of z is my x square root of x square plus y square. So modulus of inner product of x square is my this, so which is greater than equal to square root of a square, and it is equal to a. That is, if x is my 3 and y is my 4, modulus of z is my 3 square plus 4 square, that is 25. 25, it is 5, no, but here I can write this is equal to 4 square, greater than equal to 4 square, that is 4. Okay, this is the case. So in place of this, I can write this twice here. Real part, we know if z is a complex number, then its sum with the complex conjugate will give us twice the real part of that complex number. Here, this is my complex number. This is the conjugate of the complex number. Here I am getting to, twice the inner real part of the inner product of x comma y. Okay, so this is the twice the real part of inner product of xy is this one. So I am writing here twice a. Okay, that is my twice a. Twice a. Now from this equation I can write it norm of x plus y. X plus y, this is a square. Norm of x plus, here there is a square. Norm of x plus y square is equal to norm of x square plus twice real part of x, inner product of xy, real part of inner product of xy is my a, twice a plus y square is less than equal to 2. Now in place of a I can write this one, that is norm of x square plus 2 modulus of inner product of x comma y plus norm of y square. By using Schwarz inequality, in place of this modulus of inner product of xy, I can write this one. I can write this one. Okay. So in the next step, I can write this as less than equal to, this is less than equal to, this is less than equal to this one. Okay. Less than equal to norm of x square plus 2 norm of x, norm of y plus norm of y square. Using a plus b whole square formula, this if I take this as a and this as b whole square, this is a square, this is twice ab, so Using a plus b whole square, I will get this one. What is a? Is my norm x plus norm of y whole square. So next step is this one. Since norm of x plus y is greater than equal to 0, and before writing this, you must know that norm of x is greater than equal to 0 and norm of y is greater than equal to 0. So their sum is greater than equal to 0. Therefore, we have this one. We have this 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 one. Thus, by view of property 1, 2, and 4, we can conclude that every inner product space is a non-linear space. What is non-linear space? First, you must understand what is non-linear space. This is a non-empty subset. If I define a norm from X to R, then this X is non-linear space if this norm satisfy norm of X is greater than equal to 0 for all X belongs to X, and norm of X is equal to 0 for if and only if X is my norm null vector. Number 2, if alpha is equal any scalar, alpha is any scalar, then this is modulus of alpha norm of X. Number 3, norm of x plus y is less than equal to norm of x plus norm of y. Then this x together with this norm is called norm linear space. Okay, x is a non-empty set if this is a norm is a function from x to r which satisfies the following three conditions, then x along with this norm is called non-linear space. So here X is my inner product space. We define norm from X to R such that a norm of X is equal to square root of inner product of X comma X, which satisfy property 1, property 2 and property 4. Then this inner product space is a non-linear space. So in exam you are asked to show that inner product space is a non-linear space. First you should consider X is the inner product space and define this norm and prove this three property 1, property 2 and property 4. Then your theorem will be proved. Okay, number 5. What is number 5? Number 5 is my norm of x plus y square plus norm of x minus y square is equal to 2 norm of x square plus 2 norm of y square. Norm of y square here. Norm of x plus y square is my inner product of x plus y comma x plus y. On expansion I will get this one, inner norm of x square plus inner product of xy plus inner product of yx plus norm of y square. Again expand this one, norm of x minus y whole square which is equal to x minus y comma x minus y. On expansion we will get this one, norm of x square minus inner product of x minus inner product of y plus norm of y square. So if we add this two, then left hand side will be this one, norm of x plus y square plus norm of y x minus y square. In the right hand side it will be, these two will cancel out, the remaining will be twice norm of x square plus norm of y square. That is in an inner product space, norm induced by inner product space hold parallelogram law, whereas in norm linear space norm does not hold parallelogram law. That means every norm linear space is inner product space provided its norm satisfy the parallelogram law. From property 1, property 2 and property 4 we get the following theorem, that is every inner product space is norm linear space. I have already explained why every inner product space is non-linear space. In exam you are asked this theorem, then prove that. First define the inner product space, then define the norm, then prove the property 1, 2 and 4. You will get the proof. Next, the inner product space in an inner product, the inner product in an inner product space is a continuous function. How to prove this one? This one we are going to prove it by using sequential continuity. That is, f is continuous at a point, CTS stand for continuous at the point x equal to c, if and only if xn converges to c, f of xn converges to f of c. So here my function is inner product, okay, inner product and x. Let x comma y belongs to x cross x and x and y be a sequence in x cross x, Cartesian product of x, such that xn comma yn converges to x comma y. Now consider the inner product of xn comma yn minus inner product of x comma y. Here I am adding and subtracting the same term, that is minus inner product of xn comma y plus inner product of xn comma y. Then I am rearranging the term. I am writing this with this one and this with this one. And again using the properties of inner product space, I can write this one, this step, that is equal to modulus of inner product of xn comma yn minus y plus xn minus inner product of xn minus x comma y. Again using the property of modulus, I can write this step, that is this is less than equal to modulus of inner product of xn comma inner yn minus y plus modulus of xn minus x comma y. This is less than equal to norm of xn, norm of yn minus y plus norm of xn minus x norm of y by Schwarz inequality. This is by Schwarz inequality. By using Schwarz inequality in place of this modulus of inner product of this, and modulus of inner product of this, I am writing this one. Since xn converges to xn yn converges to xy, xn converges to x and yn converges to y. So from 1 this inner product as xn converges to x, so xn minus x converges to 0. Similarly yn converges to y, yn minus y converges to 0. So this will be my 0, this is equal to 0 and this is equal to 0. 0 into norm of xn and norm of yn is 0. So this converges to 0 as and tends to infinity. Okay, so that means inner product of xn yn converges to inner product of xy. Therefore norm is a continuous function at x comma y. As x comma y the ordered pair is arbitrary, it follows that norm is continuous at everywhere in x cross s. Next is polarization identity. For a real inner product space, we have norm of x comma y is equal to 1/4 within bracket norm of x plus y whole square minus norm of x minus y whole square. And for complex inner product space, we have following. For real part of inner product space, xy is equal to 1/4 of norm of x plus y square minus norm of x minus y square, and imaginary part of norm of x comma y is equal to 1/4 of norm of x plus I y square minus norm of x minus I y square. Take norm of x plus y square, which is equal to inner product of x plus y comma x plus y. On expansion, I have already explained you how to expand this inner product space. We will get norm of x square plus inner product of xy plus inner product of yx plus norm of y square. Again take norm of x minus y square, which is equal to inner product of x minus y comma x minus y. On expansion and simplification, I will get norm of x square minus inner product of x y minus inner product of y x plus norm of y square. Then I will subtract this from this one, this one. I will get left hand side as this one, and in the right hand side when I subtract this from that one, I will, this will left as it is, this will multiplied with a minus, this will be minus, minus become plus, minus become plus, and this will be minus. So from here this term will cancel out, this term will cancel out with this term, and this will be your twice of inner product within bracket inner product of x plus y plus inner product of y comma x. From the second axiom in the definition of inner product space, we know that this is equal to this one. That is, inner product of y comma x is equal to conjugate of inner product of x y. From the property of complex number, that is a no, inner product is a complex number, complex number, complex number. So by property of complex number, z plus z conjugate is always twice the real part of z. So using this property, I will get this one, twice the real part of inner product space. This is equal to 4 times the real part of xy, as here my space is real. If z is real, if z is real, then we have z conjugate is equal to z. Okay, real part of z is equal to z. Real part of z is equal to z. That is this. So 4 times of inner product of xy. Next, modulus, norm of x plus high y square is my inner product of x plus high y comma x plus I y. On expansion, I will get this one. We have uh, expand this in this way. Inner product of x with x, inner product of x with I y, then again I y with x and I y with I y. I will get this step. In the next step, I am writing inner product of x comma x is equal to norm of x square. Here I am taking I outside, then I will be I conjugate of I within the inner product. It is x comma y. Again I am taking I outside from this inner product. This will be I inner product of y comma x, and this will be I'm taking I outside. First, for the first element I will get I, for the second element I will get I conjugate, and for then I will left with inner product of y comma y, that will be the norm of y square. In the conjugate of I square minus I, first first term will left as it is. In the second term it is minus I. Then in our product of xy, in here it will be I into this will be the, by using second axiom in the definition of inner product space, inner product of y axis will be inner product of y comma x comma y. This is x comma y. So plus I conjugate will be the modulus of I square inner norm of y square. Then this is no, this is norm of x square minus I inner product of x comma y plus I inner conjugate of inner product of x comma y minus the value of this one is minus I. Value of modulus of I square is minus I, minus 1, that is minus norm of y square. If I take right first term, which will be remain as it is, that is norm of x square, minus take I common, then I within bracket inner product of x comma y, then if I take minus common, then it will be minus, I am taking minus I, okay, minus I, then within bracket is this inner product of x comma y minus conjugate of inner product of x comma y. Then this is minus of norm of y square. So this in the next step it will be twice I. This difference will be twice I imaginary part of inner product of x y. Why? If z is my complex number, if I subtract conjugate of z, then it will be my twice I imaginary part of z. Okay. By using this, I get this one. This is complex number. Subtract from it, subtract the complex conjugate. I will get two time imaginary part of I into imaginary part of the inner product of x y minus norm of y square. Then this will in the next step it is norm of x square. Here I into I into I will be my I square, and I square is my root over minus 1 square, and this is minus 1. So minus minus will be plus. This is 2 imaginary part of inner product of x comma y minus norm of y square. Similarly, you can expand and simplify norm of x minus I y whole square. You will get this one, this value. Norm of x square minus 2 imaginary part of inner product of x comma y minus norm of y square. Now I am subtracting this value from the first one. Subtract this value from the first one. In the left hand side, I will get norm of x plus I y square minus norm of x minus I y square. From this, if I subtract this one, this will minus, this will plus, this will plus. So this and this cancel with this and this. This is plus minus. Then here it will be minus plus. And what I will left with 4 times the imaginary part of inner product of x y. Divide the equation, I will get it. Divide the equation by 4, I will get this one. And these are known as your polarization identity. Okay. Now Hilbert space. A complete metric space is called a complete inner product space, not metric space. A complete inner product space is called Hilbert space. That is inner product space which is complete with respect to the metric given by dx comma y equal to norm of x minus y, which is equal to inner product of x minus y comma x minus y to the power 1 by 2 for all x y belongs to x. Next, take an example of Hilbert space. Consider the unitary space Cn. This is a Hilbert space with respect to the inner product given by this. Inner product of x comma y equal to x1 y1 conjugate plus x2 y2 conjugate plus dot 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 xn yn conjugate, where x equal to x1 x2 dot 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 xn y equal to y1 y2 dot 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 yn belongs to Cn. Next is isomorphic inner product space. Two inner product space x and y are said to be isomorphic if and only if there exists a mapping f from x to y such that f is linear bijective and satisfy this condition, that is inner product of f image of x comma f image of y is equal to x comma inner product of x comma y for all xy belongs to x. That is two inner product spaces isomorphic if f is 1 1 on 2 and linear, which in addition to this it satisfies this inner product. Okay, inner product of fx is comma fy is equal to x comma y for all x comma y belongs to x. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.